Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, I'm going to talk about fixing global warming gradually part 7. And this time we're going to focus on energy storage. So let's dive deep into it. So what exactly is the problem? Well, if you had paid attention to the news cycle, so to say, and over the course of decade, you must have noticed in the early 2010 and 2015 kind of that time zone, everybody was talking about it's like, yeah, renewables is good and all, but it cannot actually power everything. And be mindful, go even further than that. As in like from 2005 to 2010, everybody knew solar existed, wind existed, but nobody was taking it seriously. And common prevalent wisdom of that time was that these are good for remote communities or for niche cases, but they were never going to provide enough power. However, if you had paid attention now, as in from 2015 to now, you must have noticed that more and more people are talking about energy storage rather than how the heck we're going to get the power. So what changed? What changed is basically solar and wind has mathematically proven at this point in time that they can produce then more than what we can consume, flat out. It's like if we go all in, like just go YOLO, basically dump 30% of military budget into this, go YOLO on it, yeah, sorted, like flat out. It's not even a discussion. We have data about this now, that if we go all in on solar and wind, it's gonna overproduce more than our energy consumption, flat out. It's not a discussion anymore. However, there is a glitch, tiny glitch in this. That glitch is, it's not aware of our needs. So wind is not like, bro, I got you back, you need me, I'm gonna make love to you right now. But it's like, no, it's like completely different. This is a power graph of a wind farm, and each line is a different month. So you can see, like, some month you're making GG amounts of power, you are crossing 1 gigawatt, awesome. Sometimes you are touching zero. Yeah, in November it's really bad. November, and which is the other month? February. I have no idea why February is this bad, but you get the point. November and February is like zero. So that's the issue. We have the energy, source is there. It's just that it's working on its own clock rather than our need clock. Like, we need it now. Wind is like, I got you back. No, it's not like that. That's the biggest issue. And our grid was designed in such a way that it's supposed to run 24 into 7 into 365, meaning you cannot be like time of day directly affects your electricity uses. Nope, sir. Grid has power. That's all we are accustomed to, where it's like grid equals power. And what about time of month? Basically, people are not expected to be like, hey, which month is this? Yeah, September. September is like, consume as much energy as you want. And in basically November is like, nope. That's not how people work. So reality is we need 24 into 7 into 365. And this is a very popular graph. And this is a very good illustration how powerful solar is. This is the easiest way to show people that it is powerful. You start back in the old days of 2015. People are first time noticing that duck curve. Basically, people started to put solar, enough solar was added that was like, there was a dip. The dip is before the evening, solar has been contributing enough energy that there is a bit of dip, and then there is a rise that exceeds 20 gigawatt. Now this is 2015, mild pattern can be observed, okay. 2016, now significant pattern can be observed. It's like, okay, it's going down, okay. That's significant. Then you come to 2017, it starts to go really down. This is the time where every Tom, Dick and Harry talks about duck curve. Then it goes down 18, 19, 20, 21, and in 2023, as in this year when I'm making this video, it goes into negative. What does negative mean here? Meaning at this point in time, from 12 p.m. to 3 p.m. in that time zone, there was no draw on electrical grid. Solar was overproducing. No draw, meaning if California was well connected with other electrical utilities, as in like other parts of the nation, they would be selling electricity at this point in time. That much. And what is the scale? Gigawatt. We just dumped it all, like, bam. Think about this way, like few years ago, that's why I said, like, even in 2015, if you were to talk to someone, it's like, you know what, man, we're gonna drop 3 hours of power consumption of a very energy intensive stage to zero. People are like, man, pass me the joint, man. Like that, nobody would have believed you. Nobody. Like, this is another example. This is from 2012 of Germany's energy consumption. And you can see there is a little bit of solar. The solar is adding a bit of peak there, but it's not too much. Like, here's the, now you pay attention. The nuclear have been poofed, and you will see sun is going down. What is happening here? What is happening is the percentage of energy consumed is coming from sun. Like, the coal is only there to like buffer it out. This graph, 2020's graph, if you have taken a time machine and showed it to people in 2012, they would not have believed you. But it happened. And this was another reason why many times people are like, oh, why did you close down nuclear? Nuclear does not like to be throttled there is no off position in nuclear reactor. Even if you scramble the reactor, let's say some emergency happened, you're like, bam, scrammed. Does not mean it actually turns off. It simply means you have stopped the reaction and now you run the coolant. How long? A few days, sometimes, or maybe a month to really bring it down to the safe level. So there is no off in nuclear reactors. So nuclear reactors are inherently designed to run at max load, like not even max load, like they will specify at the design phase 70 or 80% of their throttle value all the time. So if you had nuclear like that, when solar overproduced, that would have created a cascade failure where they had to shut down solar just so nuclear cannot go into the red zone. So all of this data, real world data, is creating a scenario where market needs a big ass tank where we can store the energy. Be mindful, this is happening this year. Imagine what we can achieve 2-3 years from now. Like this 3-hour window can easily be stretched to 4 or 5-hour window. Imagine 20 gigawatts of 5-hour window. And if we have storage, then we can absorb more of it. And then the evening peak, we can slow it down. It's like, bro, got this. This can be done today also if people in this area is very rich. If everybody jumps into basically having on-site energy storage, small batteries, lithium-ion batteries and all that, I'm pretty sure the evening peak can also be reduced. And you can notice that old time evening peaks were much higher. Now it's lower. So it can be done. So market is ripe, as people say. So how do we solve it? The step one is overcapacity. So if we need 10 gigawatt, we have to make 30 gigawatt. We have to. We just have to. That's the bad part, but we have to. It's like we have to design the ecosystem, especially wind, because wind is one of those things that, yes, in the worst time it produces very little, but produces something. Solar is like, nope, at night. So we need something, more specifically wind, that is designed to be so overproducing that at worst case scenario, it still takes care of our base load 24/7 into 365. Not exactly this much, not all the time, but it has to be there. Like in case of countries like India, we do have the luxury of hydro dams. So, and even USA, most places have hydro dams. So hydro dam and wind can be there as a backbone. And hydro dam can be throttled if designed properly, or some modification has been done. You can design the reservoir as a long running recharging battery. So you stop the drainage when you have overproduction during the sun time. During evening, you let the drainage go. Or when wind is not producing adequately, you just let all the water go. So we need a lot of overproduction. So basically, right now we are in this sort of phase, peak demand, and whenever base load is exceeded, peak demand is created. What do you do in peak demand? You fire what we call peaker power plants. These power plants are generally jet engine power plants running on natural gas. They spool up very quickly. They start to dump energy very quickly, like bam, energy. Now, what we have to go to is this. Basically, instead of demand, we have to be overproduction, where it's like our base load is at worst case scenario, we are still producing enough. That's what we have to do. We have to create offset. Now, you combine all of this, what happens? What you get is what we call wastage generation. This has happened. Be mindful. Whenever you're seeing that line touching zero, that simply means there was a phone call made from a grid dispatcher to another power station. It's like, hey, you have to turn off the power. And generally, this call will be made to basically a solar farm or a wind farm, where it's like, bro, shut it down. Power curtailment. And that's a really problematic especially for solar. Solar has a basically lower priority. Basically, they will shut down wind first, then they will shut down solar. The reason for that is very simple. Sun is only going to work in the daytime, so you might as well use it. And they're not going to make money at night. So wind, there is some probability is going to work. So they're like, hey, wind first, and they're still overproducing, then the solar plant will get a call, which they do not want to receive, because that time simply means they're not going to make money. They're going to lose money at that point. So wasted generation, that's the penalty of it. So all this situation combined, this duck curve, overproduction, what does it mean? What does it mean? So whenever world change, generally there was two primary reasons behind it, or one of those primary. First primary reason could be scientific achievement. World figured out steam, boom. And sometimes it could be economical. World figured out this, and then it's like, whoa. So these sort of things generally happen, where you have either scientific innovation or economic opportunity, where the market was like just ready to milk. And this situation is creating a scenario where energy storage is ready to be ripped. Basically, the company that cracks this is going to print money like there is no tomorrow. So this is the overcapacity part of it. So let's look at small scale. Now, small scale, thankfully, because of the recent research and development from 2015 to now, not even 2015, 2005, let's say, battery chemistry has improved a lot. Meaning, back in the old days, we did not had any, like you can have buy a very old 18650. Just look into like 18650 from the early days. You will barely find 500 milliamp hour, 800 milliamp hour. In today's time, same cell's capacity, physical size 18650, you can easily get up to almost 3 amp hour, 3000 milliamp hour. That's how much our chemistry has improved. Like look into 18650, because that standard is ancient, and that was the one they used for Tesla Roadster. So look into that, and that will give you a actual realization. Whoa, we have actually become so good. But you have to look over decades. Then only you're like, whoa, that's a big jump. So improved a lot. Now, where does chemical batteries lie? Chemical batteries lies at megawatt hour capacity, meaning your tank size is megawatt hour. Now, there is one good news about basically these sort of tank. Their valves are huge, meaning even though they can only store, let's say, 1 megawatt hour of capacity, they can dump at like 10 megawatt, 20 megawatt, 100 megawatt. Yeah, they can go that high. As long as inverters can bear the load and transformers can absorb it, they're like, we got this. These things are like almost close to capacitor. So dumping capacity is super huge. So that's today, and as of now, when I'm making this video, they are reaching cost effectiveness, meaning it actually makes sense. Be mindful, can you make it bigger? Of course you can make it bigger. Then it actually starts to harm you. So there is a sweet spot where all the cost, quote unquote, land requirement, everything just lines up just right. In that just right phase is around megawatt hour kind of scale. Bit more, bit less, depending on your energy cost and all that jazz, but that's the sweet spot. Lifespan is good enough. Is it perfect? No. Is it good enough? Yes. Now, that itself is like, okay, but what makes it sweet is response is quick. What does that translate to? That translates to you build this puppy, and this can be utilized as what we call Hertz stabilizers. As in, whenever you are drawing power from the grid, what's happening? You are magnetically leaching energy. Basically, you turn on something, it leaches energy. Now, where does that energy go? It came from the transformer. How did transformer got it? It got it from bigger transformer. That bigger transformer, it got it further transformer. That further transformer got it from magnetically coupled rotor of a generator. That's how grid works. Now, here's the rotor will start to slow down. Now, generally what happens, the frequency starts to go down. Let's say in case of India, the frequency will go down from 50 hertz to a little bit less, let's say 49.995. Now, the moment computer detects that, computer is like, whoa, this is bad, opens up the steam valve, let the turbine spools up. But here's the deal. What if turbine is already maxed out? Meaning you do not have, like, again, generator does have some overcapacity, but it cannot be like, oh, 500 megawatt generator can produce 600 megawatt. That's not going to happen. So what do you do then? Then your frequency reaches a hard limit where it's like, dude, we do not have more generators going YOLO on it. We are reaching hard limit. Your frequency suffers. At this point in time, a decision has to be made. Either you cut load or you cut generation. Now, if you wait too long, generation will be cut automatically. There are fail-safe built into it because these generators are synchronous. Frequency going low in frequency, that's bad. If like it goes really bad, like as in like 47, 48, yeah, no, that's just nope. It will auto trip all that. Now, imagine auto tripping situation where your whole grid can go down simply because that was the peak load. Everything else could not carry the load because all of that are maxed out. So the load shedding is done. Now, what do you do at that point in time? You employ this. What's the benefit? This sort of event only happens like, once a while, weekly, so to say. And again, if you are really good in terms of energy management, you will know when this is going to happen. This is the job of basically grid operator, to know when this sort of event happens. What they will do is like charge this puppy. When there is overproduction and less consumption, they will charge this puppy. Yeah, slowly charge it, slowly. Take your time, chill, man. Take your time, eat your time. The moment that peak power happens, where it's like, dude, all generation capacity, this is like, I got this. It dumps a lot of energy for a few minutes, just minutes. But it's more than enough where generators are like, I'm good. Surge power goes away, and then it's like, everything is fine. Grid is happy. The frequency is stabilized. This is what Elon Musk did in Australia. So this is a very good use case of the super fast response time of these puppies. Where people are like, awesome. And this also means grid is actually far more stable, far more responsive, because you have extra basically oomph that can be dumped on notice, and extra reservoir where you have like, hey, we have overproduction. Again, instead of just turning off basically generation, you can be like, hey, generation, keep working, dump the energy into this. Because many of the generation, if you cut it off, it takes times to spool back up. You may not want to do it. So it's a really good, from an economics point of view, it started to make sense now, as in 2023. So that's why you will see more and more of these coming out. On top of that, this is here, this is real. We are talking about electric vehicle. Electric vehicle is slowly starting to reach market. They are reaching as high as like, 5% penetration. I'm talking worldwide. Like actually it's even less than that, but you get the point. It's actually here, it's a real. What does that mean? That simply means we're going to have insanely large amount of second-hand batteries. Now, these second-hand battery are not good enough or healthy enough, quote unquote, to be a car battery. But they are still alive. They are still like, they could be retaining almost 80 to 70% of their grand total capacity, and their surge power would have compromised a lot. That's the first thing that you lose in these sort of battery, surge power, as in like if it could dump like insane amount of kilowatts hour, it will like, hey, dendrite formation have happened. Let's chillax. So does that mean these are useless? For cars? Yes. For energy storage? No. These are like shut up, attach it, take money. So this is a very good use case for second life of EV battery, and more we're gonna do this. It's gonna be a desirable side effect, so to say. So that flat out is good. Then we have to come to microgrids. Now, what is microgrid? Microgrid is basically wherever you have a group of people stuck in a position where they cannot get energy from a grid. For example, Boca Chica, when SpaceX was building it, they were like, dude, there is only one 11 kV line. That's not good enough. So they built a solar farm and they put battery there. That's how they were running. Then they keep adding generator. Again, the solar panel could not be increased to the large capacity, and it's a giant rocket site. So they do, now they are entrenching very high voltage, as in 33 kV, if I'm not mistaken, 33 or 66 kV three-phase line. Right now, that's what they are doing. But that micro island situation is common, surprisingly common everywhere. Where it's like you could have a remote community where they do not have any power line, or there could be one power line that's just to say that it has power but it's useless. At that point in time, you're like, put solar, put wind, and put this, done. You have a microgrid. Of course, you will not have the resiliency and the oomph of a full-fledged grid, but you have a grid. And if done correctly and you design the system properly, as in like where you have critical loads that should not be turned on, let's say critical load, you could have a pharmacy. In a remote area, pharmacies are very important. So pharmacy's refrigerator would be classified as, absolute load. It will not be cut down. Then you can have hospitals, those will like, this will not cut. Then you have parks and all that, those will like, dude, if we are reaching dangerously low energy levels, let's just cut it off. And with better weather tracking that we have right now, you can really be damn good that you can have a battery bank and you're like, dude, this area is sorted. Of course, you will still have generator, just in worst case scenario. So this is small scale that we have already sorted, done. Then we come to the large scale. That scale is like, okay, good, that makes your grid healthy, but does not actually take care of the problem. Then we come to the large scale. This is where you take care of the problem. So we start with closed looped pumped hydro. Now, what is pumped hydro? Pumped hydro, basically you pumping water up, then you're letting it come down. It's using gravity as a potential energy storage for you. You put it up, so there is gravitational potential, you let it discharge, you get energy out of it. It works, done. Now, closed loop simply means you are not using it with a river. If you are doing this with a sea, it still makes it basically sort of closed loop, because again, sea is not going to run out unless it's like a landlocked sea. But whenever you're talking about like ocean, if you're attaching to ocean, nobody's going to call it a closed loop system, as in like open loop system. It can be done, but most of the time, if rivers were done, it was causing a lot of damage, because again, lot of water with a river, you can dry a river drown. So closed loop is the very critical aspect. Closed loop simply means you have two reservoirs that is completely detached from everything. And this also gives you freedom, where it's like, oh, what water source? No, you just have to import water once or twice, or if that area rains a lot, it will autofill every time. So closed loop, that's what we are talking about now. How old is this technology? Well, this is ancient technology of 1930s. The earliest one was built even further than that. And by 1930s, there were more of these, as in like not just one piece, multiple of these pieces. And as we got better in engineering, back in the days, they had like a turbine stage and a pumping stage. So pump was completely separate from turbine. Nowadays, all of them is just one thing, one physical thing. So manufacturing cost is gone down drastically. So what kind of power we are talking about? We are talking about gigawatts of power, as in there are many working plants that can easily dump 1000 megawatts continuously for hours, not just like 1000 megawatt, 5 minutes later, I'm done. No. It's like, I got this. Like from a tier 2 or tier 3 cities, they can be like, dude, I got this. Don't worry about it. I got this. And in some edge case scenarios, it has happened. It's a real world. This actually did this, where America lost a grid. Grid was like off, done. So how do you jumpstart a grid? Who has that kind of power? Nobody. These were like, I got this. They started to run water, megawatts of power, everything was isolated. They sent the power to main coal power plants, they started to spool up. Then that power was sent to other power plants to starting all of them up. Then they started to restarted the grid. So it's actually reliable, time tested, again, time tested. Gigawatts of power, that's a good part. Another aspect, gigawatt hours of capacity, meaning they can, let's say you can easily physically build right now where you have 2 gigawatts of basically power, and 20 gigawatt hour of capacity, meaning it's gonna run for more than a day at full load. So these things are big enough where they can actually absorb solar and wind and still have enough oomph left where it's like, I got this. I got this. This is, I'm talking about today's technology, not some future technology. It's like, it's here. It's real. It's been built. And they do not have any life limiting component. As in, nothing in their design is like, I'm going to go poof after a certain amount of time. No matter which battery you look, the moment it touches chemistry, it has a poof time. It's going to be poofed after some certain while. Here, it's not. All you have to do is maintain them, especially with basically closed loop systems, and especially closed loop systems that are running on what we call fresh water. There is no loading on it also. Basically, when you're talking about a dam has to go through a lot of loading where it's like, lot of like, it has to handle rainwater, flooding and all that. Just it has to handle that. So a lot of loading is there. This is like, bro, reservoir, just don't worry about it. So flat out, if you can maintain it properly, it's gonna run for centuries. Like, there is no discussion about that. That's sorted. Be mindful, many of them are actually ancient at this point in time. So we know, like, this is there, and it's a closed loop, so it does not harm the ecosystem. That's another bonus. Now, how many of you, this sort of puppy you will need to take care of a nation? If you have enough overproduction, enough solar, enough wind, this you will need, like, let's say hundreds to take care of a country. Like, this is American one, these are European ones, and this is Chinese one. You get the point. Like, basically, if you have hundreds of these, now can you actually build hundreds of these? Easily, especially closed loop. In open loop system, we had a limitation because you have to find a river. Now you don't have it. You just have to find physical gradient. And if you are strong enough and able to be lucky enough where you can have a cliff, like this is a cliff, this is the ocean. So they have a cliff sort of face. They are like, down they are using. The height difference is not that much, but if you are in a lucky position where you have ocean and very large, like, large amount of cliff, oh, you're gonna be making money. And be mindful, this technology actually got its resurgence just after nuclear, love, because everybody was like, nuclear is the future, man. Like, I think that was the slogan in America. It was like, power too cheap to meter. They were like, fixed cost, man. Who's gonna bother to meter it? At that time, this problem was, put forward, where it's like, dude, how the heck you gonna add that much nuclear power plant? Because if everybody adds nuclear power plant, the base load keeps going up. It reaches a point where it's like, what the hell you gonna do at so much surplus production? You have to cut cost, cut production, and you can't just cut production in a nuclear power plant. So what can you do? So somebody came in, let's bring that down and run these sort of things. What the idea was is like, during night when you have overproduction, this puppy is gonna absorb the energy. During daytime when you have peak loading, this is gonna dump the energy that it has absorbed. And these things can have very high efficiency. They can exceed 70% round trip efficiency. So it's actually good. And modern designs can even cross or even touch 85%. So what does that mean? That simply means they could have fewer nuclear power plants and still have more than enough reserve capacity to handle any transient spikes and absorb overproduction. So this is a known, tested technology. I am genuinely shocked. Everybody's like, what, we need batteries, Dude, we have this. Just bring this to public attention, make this publicly, it's like, oh, this is what we're supposed to do. Problem solved. This is large scale. Small scale, sorted. Large scale, we have to rediscover it and then sort it. Be mindful, close loop. Do not touch a river. Touch a river, it booms. Do not touch a river. So what we can expect in the future? Well, reality is 2022 has given a world a very amazing outlook. Why? That was the first time our power draw went up. Okay, that does happen. That's a regular thing. Year over year, our power draw worldwide is going up. Here's the deal. Our emission for power, let that be very clear, emission for power actually went down. How the heck that's possible? That's, last year was the first time 10% of global energy came from renewables. Now, you may be like, I'm talking about 100% here, and that fact that I'm providing, it's only 10%. It's like, but here's the deal. 10% of worldwide energy. If wind the clock back, that's the whole world's power consumption. But here's the wind the clock back as early as, let's say, 2010. Talk to anyone and say that that's happened without fusion. Nobody would believe you. Nobody. We have achieved it, and the data concurs it. It's like people who are actually bold enough to risk solar, bold enough to risk wind, they are proven correct. It's like, bro, it is here, it's real, it works. Science is clear, engineering sorted, economics makes sense. So can we do 100% renewable? Engineering wise, yes, today. What's the limiting factor then? Money. As in, like, if USA wants to do renewables, all they have to do is just like relax the military for 2-3 years and then like sorted. And it's not even like a nuclear power plant which takes 10, they will say it will be built in 10 years and it's going to take 25 years to build. It's not even like that. It's like, bro, solar farm, built, go. Cost for the grid. Again, that's like what, one F-35? So it's one of those things. Money is the only limiting factor. On top of that, there is another good news. The good news is rising fuel cost. As fuel prices going up, either because of OPEC or Putin going YOLO, both of these things create what we classify as uncertainty. Uncertainty makes these things far more reliable. Now, like, wait a minute, how the heck one uncertainty make this uncertainty more desirable? This is under your control. Nobody in OPEC is gonna decide. It's like, bro, give me F-35s. If you don't give me F-35s, prices go up. Is it like, give me Ukraine, or the prices go up? So, like, look at the gas prices. Holy damn, they did freak out. It's like, nah, normal ups and downs. So, be mindful. In those sort of scenarios, this is like, dude, this is in my control. I know what kind of power we can expect. And be mindful, our weather modeling, that's why I said we have 10 years data now. Our weather modeling is like, wind farms can give you a graph that we're going to give you this much power in future. And it's surprisingly, horrifyingly accurate. It's like, have you ever wondered what the heck happens to all the weather satellite data? Ask them. They're like, yeah, we are the actual consumer of that data. So at this point in time, flat out science is clear. And yes, we have to build overcapacity, but it's like, yeah, overcapacity and all that. But here's the, in the early days of 2010, if you wanted 1 megawatt hour, solar would have required you around $378 per megawatt hour. At that point in time, coal would have required $111. This is like, ancient times of 2010. Here's the, what about now? As in 2019, ancient times. Coal was 109. It goes up as coal mines are being drawn up more and more. The prices are going up. So 109 was actually a dip. Now it's actually going back up. How about solar? Solar went from 378 to 68. That's a missile drop. That's like, and that's why I said from 2015 to 2023, the fact that, like, California just dipped is like, nope, too much overproduction. That just happened. This is very recent. So that's why I'm so confident about that 100%. And from economics point of view, from a country's point of view, what would you rather have? Renewables that you control and with good management and good understanding, with some overproduction sorted, or rely on OPEC to do their part, and rely on Putin or people like Putin. So it's one of those things, and overcapacity is cheaper. It's not going to hurt as much as it used to because it's cheaper. It's like, ask someone, it's like, oh, we have to plant 1 or 2 megawatts of extra capacity. It's like, okay. It's like, oh, it's going to cost $5 million. Hell no. Now it's like, it's going to cost $500,000. It's like, okay, painful, but manageable. It's going to hurt less. And be mindful, this is a game of chicken and egg at this point in time. So countries that are investing in renewables now, they're going to be in much better position. Why? If the prices of fuel goes up, which, be mindful, track decade over decade, it's only going up. So at that point in time, in future, we're going to have even more expensive energy. At that point in time, what will you do? You cannot cut power, and you cannot invest in renewables because you are spending all your money into basically fuel-based system. So every country, it's in best interest to jump into renewable now. This bitch slap, again, be mindful, China also bitch slap the world, OPEC also bitch slap the world. This sort of bitch slapping is kind of awakening Europe to where it's like, no, we really have to do this. We really have to get into this. And once floating, wind turbines comes to fruition, be mindful, it's real, it's here, it's just not mass produced. Heck, even China is dumping into it. It's like, bro, we gotta get this puppy working. Once that is sorted, we are looking into a world where you can actually have price locked energy. That's like, energy is just locked. It's the only reason going up is inflation. So there is amazing hope in the future, and be mindful that 10%, just few decades ago, that was the whole world's energy consumption. So sometimes we kind of lose sight when it's like, oh, it's only like, 20 terawatt hour capacity. It's like, dude, few years ago, nobody would have believed you. Few years ago, before that, that was the whole nation's power consumption. And acceleration, look at the goddamn acceleration. It's like, a rocket takes time to get to orbit. It's not like, it's not fast and furious. It takes time, man. Relax. So future is amazing here. And again, pumped closed loop pump hydro, take care of the big load. Small load we are already doing. All these things combined with overproduction, sorted today. Not some future technology, not some magical fusion, today. And it's just a race now. Every country that is investing now will be like much better off tomorrow, simply because fuel prices will be higher. At that point in time, they're like, yeah, we invested well. So this was my presentation on energy storage of renewables. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.